Hello, and welcome to today's ACM Learning webinar. This webcast is part of ACM's commitment to lifelong learning and serving the over 100,000 computing professionals and students who are ACM's members. I'm Eric Meyer, CEO of Applied Duality. I've worked on the Hack language with Facebook, RX Java library with Netflix, the Dart language with Google, and many more things. In the past, I was an associate professor at Utrecht University, and I'm still associate professor at the TU Delft. I teach the Principles of Reactive Programming course through Coursera and Introduction to Functional Programming to edX. I'm also a member of the ACM-Q editorial board, and you can find more info on my background in the bio widget on the left of your screen. For those of you who may be unfamiliar with ACM or what it has to offer, here's some more information. ACM offers educational and professional development resources that bolster skills and enhance career opportunities. Our members can stay competitive in a constantly changing world of computing with a range of ACM Learning Center resources at learning.acm.org. You can see some of the highlights on your screen. ACM recognizes the role of computing in driving the innovations that sustain competitiveness in a global environment. ACM provides timely computing information published by ACM, including communications of the ACM and Q magazines, access to the ACM Digital Library, the world's most comprehensive database of computing literature, international conferences that draw leading experts on a broad spectrum of computing topics, and support for education and research, including curriculum development, teacher training, the ACM Turing and ACM Prize in Computing Awards. ACM enables its members to solve critical problems by using new technology that enriches our lives and advances our society in the digital age. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you. First of all, the slides will advance automatically throughout the event. On the bottom panel, you will find a number of additional widgets and resources. If you experience problems with the slides or audio, press the F5 keys in Windows, Command R if you're on a Mac, or refresh your browser on a mobile device. Or you can just close and relaunch the presentation. To control volume, adjust the master volume on your computer. If you have any questions during the webinar, please type them into the QA box at any time during the webinar and click the Submit button. I will organize the questions as Paul speaks, and he will reserve time at the end of the presentation to address all your questions. The session is being recorded and will be archived. You will receive an automatic email notification when it comes available, and please check learning.acm.org for updates on this and other upcoming webcasts. At the end of the presentation, you'll see a survey open up on your screen. Please take a minute to fill it out to help us improve our webinars. And you may also open the survey at any time throughout the presentation from the resources window on your screen. You can use the Facebook and Twitter widgets on the bottom panel to share the presentation link with your friends, as well as tweet comments and questions using hashtag ACMLearning, and we will be watching your tweet. Now, today's presentation is Speaking Data, Simple Functional Programming with Clojure by Paul deGrandis. Paul deGrandis is a lead developer, architect, and director of the Research and Innovation Group at Cognitect, where he helps organizations envision and execute new technical strategies centered around unlocking value with next-generation information systems. Paul has helped to produce some of the most successful companies, brands, and cutting-edge research. He has worked on next-generation cable systems, autonomous internet infrastructure, distributed search and recommendation engines, massive online social game platforms, and much more. He has also volunteered his time with Code for America and as a mentor with the Portland Incubator Experiment, and also has many open source contributions to his name, including Clojure, ClojureScript, Pedestal, PyPy, and more. Paul, without further ado, take it away.
Thank you very much, Eric. I'm Paul deGrandis, and I'm with Cognitect, a consultancy and technology company for data-first distributed systems. You can find me on the web and across social channels with the handle @oplease. Feel free to reach out with any comments and questions at any time. I always enjoy a good conversation. And I'd like to thank everyone who helped pull this webinar together and all of you for attending. This talk is Speaking Data, Simple Functional Programming with Clojure. Let's just dive right in. It's going to be a quick tour of Clojure, and we're going to discuss sort of the core ideas about Clojure. In a previous talk by Stu Holloway called Clojure in 10 Ideas, Stu said, the key to understanding Clojure is the ideas, not the language constructs. And that's because there aren't a lot of language constructs or syntax in Clojure. It's a pretty simple language. So the core ideas really make up the compelling aspects of Clojure. Everything that I say about Clojure is true for ClojureScript as well. So Clojure is a hosted language. Clojure by itself runs on top of the JVM. But there are lots of implementations across other hosts. So ClojureScript on top of JavaScript VMs, both Node and in the browser. Clojure CLR on the .NET or CLR runtime, and so on. So you could find Clojure on Scheme or Lua and so on. After we look at these core ideas and get a sense of what Clojure is really all about, we'll look at Clojure through a software engineering lens, sort of the macro reasons for choosing Clojure. Why Clojure? Why now? What are the aspects of the language that lend Clojure to solving harder, complex problems? We'll also talk about soft aspects of Clojure like the community, ecosystem, and support. From there, we'll move on to Clojure being applied to solve real-world problems. And we'll look at 3 quick case studies. The Walmart e-receipts or savings catcher system, a very large distributed system. The Boeing 737 MAX diagnostics system, pretty interesting data fusion problem. And then DRW trading, high-frequency trading written in Clojure. I have a lot of slides, so we'll move through some of them pretty quickly. But at any point, as Eric said, go ahead and submit the questions and we'll circle around at the end. So a quick overview of Clojure. If you're looking for getting started guides or guides in general, API documentations, tutorials, community information, and so on, Clojure.org is the language website. It should be your first stop, and from there, you should be able to find your answer. Clojure is a Lisp dialect, specifically a Lisp 1, and all the things that you think that go along with Lisps are very true in Clojure. It has a very small core, it embraces the code as data philosophy, and so on. It's a functional language with a very strong emphasis on immutability, and it's really a language for data manipulation. Data is going to be the front and center theme throughout the entire talk. It's symbiotic with the established platform that it sits on. It really should have frictionless interop between the host and the language itself. It's designed for concurrency and managed state. Perhaps that's what it gets most of its press about, but it's actually only one aspect of Clojure. It's a compiled, strongly typed but dynamic language with very powerful polymorphic capabilities. We'll dive into those in the middle of the talk. Specifications are first class within Clojure, which is a very interesting aspect for a programming language, and actually a relatively new feature for Clojure itself. And Clojure programs are composed of expressions, and expressions always return something. That's a very quick overview, but hidden in here are the 10 big ideas that I want to talk about. And as I was saying, you'll notice that all of these core ideas really put data front and center. As we move through the slides, you'll see that the ideas will build on each other. So let's just get started. And what better place to start than the data notation itself? Extensible data notation, or EDEN, is an extensible data format for the conveyance of values. Superficially, this is going to look very similar to JSON in shape and format, but it's important to remember that it doesn't convey objects. There is no type system, no schema, no reference types, and so on. It's for the conveyance of values. It has a rich set of built-in elements and a generic dispatch extension character. Using that extension capability, you can fully capture your domain. Now, this is really important for a few reasons. There's this incidental complexity involved in mapping your problem into the constructs of a given language. You're always forced to reframe that problem to the closest analogs that you have available in a language. This extension character allows you to fully capture domains and express domains however you need to within the language itself. And extensions to the notation are opt-in. So that means your extensions for your domain don't break my code, and my extensions for my domain don't break your code. But if our domains overlap, we can use those extensions to talk about the problem in a more fluid way. And so why do I start with Eden when I talk about Clojure? Well, Clojure programs themselves are expressed in Eden. Eden is the serialized form of Clojure. You can read more about the format at this GitHub repository here at the bottom, Eden format. All right, so let's take a quick look at some Eden here. Again, superficially, this looks a lot like JSON. Here we have a hash map. It looks to be about a person, a first name, a last name, an address. Again, a nested map here. And you might notice that there aren't any commas. In Eden, commas are a white space. So let's dive into each of these pieces that we're sort of looking at here. We'll start with the scalar types. So the scalar types, we have a string, a character, an integer, and including a big int, a floating point, and also including a big decimal, Boolean, nil, symbol, and then keywords. And we can use these scalar types and put them into collections and build up more data. So we have a list that is sequential and linear, a vector that is sequential and random access, a map for associative data, and a set for membership data. So we can see how Eden is actually used to write Clojure code here. Here we're looking at the printline function with a single argument, hello world, a string. So that's the semantics. It's a function call, a function invocation here. But this also has a structure, right? It's also just data. It's a list with a first element a symbol and the second element is a string. And for those new to Lisp, the first thing in the list that we see here, we tend to call the operation position or the action position or the function position. That first thing is always going to be a function and everything that follows it will be arguments. And using that knowledge, let's look at a more involved example. Here I'm defining a new function with defin. I'm going to pass a bunch of arguments to defin to define a function, including the function name, a doc string, the argument list, in this case it just takes a single argument, and then the body of the function, which is just string concatenation here. Now, this is pretty straightforward, but it also has a structure. It's important to realize this structure and semantics. So, there's a list with a symbol and another symbol and a string, and then a vector with a single symbol inside of it, and then the body of the function is actually just a list with some symbols and a string. Now, being an extensible data notation, I could go ahead and extend the representation however I needed to in order to fully capture my domain. We can see how that happens here in this next slide. The generic extension mechanism allows us to extend this data formation, or the data format, using the hashtag name and then some Eden form that follows. And that name describes the interpretation or the domain of the element that follows. These can also be recursively defined. Eden ships with some built-in tags. So there's the inst tag for an instance, a time instance, using the RFC 3339 format. In the middle of the slide, you can see an example of the inst tag being used. There's also a UUID tag in Eden for canonical UUID strings. Now, you can extend this extensible format to whatever domain you want. And at this point, you all know Clojure. You've seen all the syntax there is to see, and you know the general semantics of how things get called and defined. You could make a first approximation of any Clojure program at this point. But let's keep going deeper. You've seen the data notation, but what about the data itself? What about the data structures? In Clojure, all the data structures are persistent data structures. They're immutable, and change is only through function application. Change always produces a new collection type that's structurally shared with the old collection. This has full fidelity old versions. Those always remain available. And that structural sharing allows it to maintain performance guarantees. These data structures, these persistent immutable data structures, are built upon linked lists and trees. So we can sort of see a superficial example of those. Imagine that I have a linked list and some reference pointing to it, X, and I want to go ahead and add 2 more elements to it. X is still fully intact. X is still the reference to the list that exists at that point, and Y is just the reference to the list of these 2 elements, which then references the existing list that was previously there. And we can see a more involved example here of the tree style. So here's a hash map. It has 15 elements in it. Pretend that I want to add 1 more element into it. I add a new element into it, and then those elements reference the existing parts of the tree. So that's roughly how graphically you can think about these persistent data structures. And let's talk about some of their characteristics. So the things that make data difficult in the mutable world are pretty trivial or easy in the immutable world. Think about all the difficulties around sharing or distribution or concurrent access with data in some of the more common programming languages. Those things become pretty trivial. So sharing, distribution, concurrent access, the access pattern for mutable transient data always has to be eager because it might change out from underneath you, and caching becomes a pretty difficult thing. Some examples of these mutable transient data structures, the standard Java and .NET collections, relational DBs that are all update in place, and generally speaking, all place-oriented systems. Some examples of the immutable or persistent data, those are the Clojure and F# collections, the Datomic database, and generally speaking, value-oriented systems. The limitations that demanded the use of place-oriented programming are gone. We have a lot more RAM, we have elastic computing, we have a lot more compute capabilities. So we no longer have to deal with the restrictions or the constraints of these place-oriented programming systems. We can go ahead and use value-oriented systems. And you can see that these ideas are getting popular in other languages. For example, immutable.js, a library written by Facebook to bring immutable data structures into JavaScript. I'm not going to go through this whole table, but roughly speaking, this table talks about how you can create, examine, and change the data structures within Clojure. All the creation functions are the word of the actual data structure itself, or the collection type itself. Examination for digging into or pulling apart or finding if something contains a value. And then change uses often conj or conjoin or associate across all the collections. Now, an interesting aspect to point out here is the polymorphic behavior of functions like conj and assoc. Right? They're polymorphic based on the type of data that they've been given. And so they can always do the most performant operation based on the data structure that has been passed in. Pretty interesting stuff. Okay, so we have these great data structures, and we can, they give us some great characteristics and great capabilities, but how do we actually build up state? How do we build up or collect values over time? In Clojure, that process is called the unified succession model, and there's a whole suite of functions that go along with this model of computation. It's strongly about the separation of state and identity. Identities are managed references to immutable values, and those references refer to some value at some point in time. Values don't get updated in place. Right? You perform operations on the references, and then that moves the values forward through time. And only by applying functions, specifically pure functions, can you move values forward through time. So these references see a succession of values. In Clojure, all of these functions related to the unified succession model follow the same format. It's some change state function, some reference type, some pure function, and then all the arguments that you want to pass to that pure function. And Clojure ships with some reference types that are very helpful to use. So we can cut these up in a lot of different ways, but let's just talk about them in a synchronous versus asynchronous manner. So on the synchronous side, we have a var and an atom for uncoordinated references, and we have a ref for coordinated changes using a software transactional memory system. On the asynchronous side, we have agents that allow us to ship off computation to them. On the right-hand side of the slide, you'll see a sort of simple model of the unified succession model. And we're going to go ahead and we're We'll dig right through that. But before we do that, think about all the incidental complexity from state management, all the kinds of bugs and defects that creep up because of the inability to carefully manage state. So maybe you're working on many core systems, maybe you have a heterogeneous computing setup. All these problems, they start to go away the moment you start to pull apart state and identity. So here I am given some value. And let's just take some function here. And then I want to atomically apply the function to the value. And we're going to call that atomic succession. That results in a new value at some new point in time. And I can go ahead and do that process as many times as I need to. If I sort of draw a box around all those values, that's a reference. And a reference sees the succession of values. Observers perceive identity. They have the identity of the reference. And at any point in time, they can get the value at that point in time. So they can see the value, they could remember that value and record that value if they wanted to. And observers don't coordinate in any interesting way. So how does this actually look in Clojure code? Well, here on the right-hand side of the slide, you'll see that I'm defining a new counter, and that's going to be an atom reference type, and it's currently going to hold the value 0. And then I want to apply addition to that 0. So I swap on that counter, applying the function addition, and passing in the argument 10. And this results in a new value, 10. We call swap the atomic succession here, and obviously addition is the pure function. But the separation of state and identity is something that happens every single day. So, imagine that today is November 8th. When I say the word today to you, you know that it refers to some point in time that we're at right now. But, there's some function that gets applied, the rotation of the Earth, that moves days forward. So tomorrow, when I say today to you, you'll know that I actually mean the day that we're on. And that's truly the separation of state and identity that exists inside of Clojure. November 8th is never going to change. It's immutable. November 9th is never going to change once it happens. That's immutable. That is the state and the identity of today being a reference. Okay, so we have the separation of state and identity. We're building up collections of values. Let's talk about computations on those values and sequences of values. Clojure is a language programmed to interfaces and abstractions. In fact, all of the persistent data collections that we've seen so far are actually defined in terms of interfaces. And Clojure, since it strongly embraces the foundation of the host and has the symbiotic relationship, uses all of the Java interfaces for interop. At the very bottom of Clojure is an interface called the sequence interface, and it unifies the foundation across all of the data. Typically in lists, the seq or the sequence is a concrete type. It's a concrete object, if you will. But in Clojure, it's actually an interface. Lots of things can be sequential or sequence-like. And so we use the sequence interface to define things that are like iterators or like generators, but they are immutable and they are persistent in Clojure. So it's better to have all of these functions operate on one abstraction and be able to extend that abstraction to whatever you need to than to have 10 functions on 10 different abstractions. So Clojure's core is actually made up of all of these data-oriented functions that operate only on interfaces and abstractions. And seeks work absolutely everywhere in Clojure. Collections, files, directories, XML, JSON, result sets from SQL, and so on. They all fulfill the sequence abstraction for us. We can dive in and see how we might use the sequence abstraction. The core interface is actually just defined in terms of 3 things: first, rest, and cons. So if you called first on a vector of 4 elements there, you would get the very first thing. If you called rest on those same elements, you would get a sequence of the rest of them, all but the first. And cons, or construct, allows you to construct new sequences based on one element in a following sequence. Take and drop allows you to take elements off the front of a sequence. So take 2 elements off the front and you would get a sequence of just the first 2 elements. or drop the first two elements, returns a sequence with the remaining elements. And these sequences can be lazy and infinite. So in Clojure, there's a function called iterate that constantly iterates a single function on top of a value. So increment 0 here, inc0, would return 1, and then iterate on top of that, inc1 would return 2, and iterate on top of that, and so on. That would return the infinite sequence of constantly applying inc. We can also cycle data to generate an infinite sequence of some cycle of bounded data. We could repeat a single value and generate an infinite sequence of just that value. Or we could repeatedly call a function of no arguments and generate a sequence of whatever values that returns. So here I'm repeatedly calling an anonymous function, and inside of that function I'm generating a random integer, so I just get an infinite sequence of random integers. And then we can go ahead and continue the sequence abstraction. So map, filter, and reduce. There's a function range in Clojure that gives us a range of numbers, 0 to that number. You can also change the steps that you would want here. For now, we just want to take steps by 1. We could filter odd, getting all of the odd elements out of that, and that returns a sequence. We can map inc across that same range. Of course, it increments all of the numbers. And we could reduce addition across that range and get the value 45. Now, all of these sequence operations are lazy by default. They do absolutely no work until they're consumed. Here on the slide, we're looking at the results. They're being consumed by us, by the console. So we would see those results. But typically in Clojure programming, these do no work until you use the values out of the sequence. And so we can take all these pieces that you've seen so far, and then we can define the Fibonacci sequence. Here I'm defining the Fibonacci sequence to be some iteration of pairwise numbers that I want to add up. And then out of those pairwise numbers, I'm only going to grab the very first number out of each of them. So then I take the first 7 numbers out of the Fibonacci sequence, and there they are as a sequence. And notice again, now I'm going to pour those same 7 numbers into a vector. So that's how we can take a sequence and turn it into some concrete piece of data. Now in other programming languages, taking 7 elements off the Fibonacci sequence would destructively destroy those first 7 elements. But in Clojure, if you take 7 elements off a sequence and then turn around and take 7 elements off the sequence again, you would get exactly the same 7 elements. They are immutable sequences. So all of Clojure is built on top of this sequence abstraction. And it's a really powerful abstraction. It allows us to break down a problem into very small discrete steps and string them all together through the sequence abstraction only. So imagine you're given a problem like, what actors are in more than one movie topping the box office charts? We could think through each of the small steps we might do. Well, I need to find some data source for all of these movies. Then I need to download that data source or open the file somehow. I need to parse out all the values. I need to walk through each of the movies and grab all of the cast members I can find, extract them and organize them only by actor name, then create some distribution or some frequencies count of all of those actors, and then sort by the highest frequencies, and I would be able to find the actors I'm looking for. All right, so we take this problem, and that problem maps directly to small operations that we would do using the sequence abstraction. So here I'm using Clojure's thread last operator, and that just says, take some value, run a function against it, take that result, run another function against it, take that result, and run another function against it, and so on. So here I have the URL for all of these box office movies. I use Clojure's slurp function to read it in. I use Clojure's JSON reader to parse that JSON and read it into persistent data structures. I then grab all of the movies from that data structure. I grab all the cast out of the movies. I grab all of their names out of the cast. I use Clojure's frequency function to create a frequencies distribution. And then I sort by the value out of those frequencies so I can find the greatest one. All right, so if we go back and forth between these two slides, you'll notice each of those steps mapped exactly to one operation that I would be doing using Clojure's sequence abstraction. So here we see where Clojure shines the brightest, processing data, extracting values, extracting facts, finding insights, and so on. This is Clojure's sweet spot. But Clojure really embraces modern infrastructure. You know, the systems that we use today typically are many core machines. And embracing those systems, embracing that infrastructure allows us to make use of all the resources available. So on the left-hand side of the slide, you can see an example of just using the straight sequence abstraction in a very linear fashion. Imagine I have a dump truck full of apples, and I want to go through all the apples and find the edible ones, you know, throw out all the bad ones effectively, and then, okay, I've got a good apple, I want to rip off that sticker that's on all of those apples, and I want to count them all up. Well, we can use Clojure's reducers capability to do the same sequence-oriented abstractions, but on top of the fork join processing capabilities on the JVM. So this makes everything parallel across all of the cores available, and also uses work stealing from the queues. So here I have the exact same apples, but now I use the reducers version of filter. So in parallel, find me all the edible apples, and then in parallel, remove all the stickers, and then using a parallel version of reduce called fold, go ahead and count that up. So let's use all the infrastructure. You know, Clojure is a modern language about modern infrastructure to build modern systems. Let's go ahead and use all the resources available that we can. But it's not just about sequentially linear and parallel. You know, I want to have more control over my processing. And Clojure should let me have that control. You know, if it is truly a language about data processing and really operating on data, I should have as much control over how that processing happens. I want to be able to reuse, you know, recipes for processing data, you know, across many contexts, across many systems. I want to be able to decide between processing data eagerly or lazily, and so on. And I would really like to be able to compose recipes up. That would be helpful for me. And Clojure does this with a tool called Transducers. They are composable algorithmic transformations. They're completely independent of or decoupled from the input and the output sources. So they purely just describe the algorithmic transformations, the functions that you want to apply. A single recipe then can be used for many different contexts or across many different processes. So you might use one single recipe to process collections or streams or channels or observables. You can also decide on demand the transformation characteristics of a given recipe. So you get to decide between eagerly or lazily processing data per use of that recipe. And best of all, this uses the exact same sequence API that already exists inside of Clojure that we've already seen across the past few slides. It's just the sequence API without specifying any source sequence at the input. Let's just see this in action. Before, on a couple of slides back, we saw map and filter, but here again we're seeing map and filter, but just without that input source. So filter odd with no input source returns a transducer that just filters odd. And I can take that transducer and apply it like a function to any source that I want. Same with map inc and take and drop, and all of the sequence API, all of the sequence-oriented functions work this way. They can be able, you can use them to create transducers. Composing transducers together is just function composition. So here at the bottom of the slide, you're seeing that I'm building some recipe where I'll first filter odd, and then I'll map the inc function across everything, and then I'll take 5. And now I can go around with that recipe and apply it to whatever data source that I want. Okay, moving on now, let's start talking about Clojure's polymorphic capabilities. And we'll start with perhaps the most popular one, protocols. These are named sets of generic functions. They provide a high-performance dynamic polymorphism construct inside of Clojure that's polymorphic on the type of the very first argument. Specification only, there's no implementation, so it feels a lot like interfaces. And it's fully open for extension after definition. So we use protocols to solve the expression problem, for example, in Clojure. And, you know, colloquially, people call protocols, you know, the good parts inside of Clojure. And we could keep talking about protocols, but let's just see them in action. I think they make more sense when you see an example. So here I'm defining a new protocol called a protocol. I have some doc string that describes that protocol. and then a collection of functions that go along with that protocol, a named set of functions here. So I have the bar function that takes 2 arguments, and I have the baz function that takes 1 argument. And if I try to use baz on the string hello, I would get an exception. The exception would say there's no implementation method for baz of this protocol called a protocol found for the class Java lang string. So I haven't defined any implementation for string for this protocol. It's pretty easy to do though. I just extend the protocol to the string type and I write the implementation. So here's the implementation for bar for a string. It's just string concatenation. And the implementation for baz for a string is string concatenation prefixed with baz there. Now if I go ahead and I call baz again on the string hello, I would see the result baz hello. And that is just how protocols work. So an interesting side effect here though is that you can extend protocols to types that were previously defined before you, right? I define this protocol, a protocol, in my source code. Java lang string has existed for a really long time. I want string to participate in my protocol. I can go ahead and extend the protocol to the string type. So that's a very powerful mechanism. But it's not the only mechanism for polymorphic behavior inside of Clojure. We can talk about polymorphic behavior based on types of polymorphism that are closed for extension and types of polymorphism that are open for extension. So on the closed for extension side, it's pretty common to see Clojure code that uses dispatch maps. That's pretty common across all functional aspects of other languages, conditional dispatch, and even pattern matching dispatch. And the open for extension aspects of polymorphism in Clojure, we have multi-dispatch using multi-methods, and we have protocols, which is only polymorphic on the very first argument. So those are basically the choices you have for polymorphism inside of Clojure. You've seen a lot of Clojure. We've gone through these slides pretty fast, but at this point, you've seen the majority of the language. You've seen Eden, you've seen the data format. We built up from Eden to collections, so you understand the immutable collections. And we saw that those collections are all tied together by a common foundation called the sequence abstraction and so on. But everything in Clojure is oriented around data. So Stu Holloway in a previous talk said, program in data, not in text. Now that's one of the great aspects of Clojure. We program in data and not in text. Our programs are just collections of data structures. And that means that program manipulation is just data manipulation. But Clojure is already a great language for data manipulation. So I have a wonderful, very powerful programming language to shape the language itself. I can extend the language using the standard practices that I would use, functions, macros, and the extensible reader, or the Eden notation. The great aspect about this is it's possible to build the language up into your domain. What's the ideal way to solve your exact problem? How would you do that? Imagine this ideal future, and then go ahead and build that ideal future by extending the language up. You never need to wait around for the language to evolve to solve certain problems. You don't have to wait for concurrency constructs to be added to your language or lambdas to be added to your language or whatever. You have full control over adding to your language however you like. But best of all, those new aspects to the language, those just become libraries. There's nothing special about them. And Clojure doesn't have reader macros as seen in common Lisps, so it keeps things very consistent and familiar. There's no weird mini languages that really exist. So let's look at 2 examples of building libraries that add full programming models into Clojure. We'll look at core async and core logic. So core async is just about async programming using channels and CSP. But interestingly enough, there's no bytecode rewriting. Typically for async programming on the JVM, people go through all these tricks of bytecode rewriting and class reordering and so on. And there's actually no modifications to Clojure done whatsoever. The language Clojure doesn't change whatsoever inside of core async. It's just the library that adds these capabilities to the language. It's comprised of Go blocks and IOC threads, parking, all the things that you would expect. Interesting about core async inside of Clojure, though, is the separation channels from their buffers. So you get to choose the buffering capabilities that you want per channel. Here's a quick example at the bottom. I create a new channel called messages. I put the string ping on that queue on the channel. And then in a Go block, I try to pull out from the channel and I print it out to the console. So pretty quick overview. When I release these slides after the talk, all of these slides are linked to the libraries themselves, so you can dig in more if you find this interesting. But let's also talk about core logic, which brings logic programming as a library into Clojure. It gives you Prolog, relational programming, constraint logic programming, and nominal logic programming, all very powerful. It's also fully extensible to other forms of logic programming. So sometimes you'll see people use core logic as a testbed for other types of logic programming. So as you're working through your problem and you realize, oh, this problem would be perfectly solved by a logic programming system. You can do that directly inside of your library. You can do that directly inside of your program just using something like core logic. There's lots of great examples on the core logic project page, including a Sudoku solver, very interesting type inferencer, all sorts of stuff to look at. Very interesting if you're into that. But I'll give you a quick example here. So I define some relation for rock, paper, scissors of a winner, an action, and a loser. And I go ahead and I establish all the facts for my operation space here. And then interesting in logic programming that you can either start with the inputs or the outputs or some combination of inputs and outputs, and the logic system will go ahead and fill in all of the holes. So you can sort of go forwards or backwards, which is very helpful in certain problems. So run star is the operation for generic search inside of core logic, and then you go ahead and you fill the slots with inputs or outputs. Now I want to talk about an interesting aspect to Clojure that's relatively new to the programming language itself, called Clojure spec. These are first-class specifications within Clojure itself. It's motivated largely because docs just aren't enough. Given Clojure's dynamic behavior and polymorphic behavior, and given the fact that it is a dynamic programming language without static typing, docs just simply aren't enough to inform people about your programs or to enforce any sort of characteristics across your data or across your functions. So these are predicate-oriented specifications of the data themselves. And that's an important bullet because Clojure programs themselves are also data. Right? So if we can specify just data, we can specify anything about Clojure. So we're talking about values, maps, and sequences. Largely, that's what Clojure spec operates on. You can use it for validation, error reporting, parsing and destructuring, instrumentation, test data generation, property-based generative test generation, and so on. These are all the this is the tooling that we've been building up around Clojure spec. And we can just see a quick example of Clojure spec here. This is a very large example. You're not meant to sort of parse all of this, but you can sort of see that we can define these specs to be named predicates, and then we can combine them up in any sort of fashion that we want to. Halfway through that slide, you can see scat, and we're basically saying, yep, so there's going to be a sequence where we expect the sequence to follow this order, some concatenation of these elements. So first the number 42, and then some number of odds, and then I expect there to be a map with some keys in it, and then I expect some any number of O's or odd numbers, and so I basically want to break up odds and evens, and so on. What's great is when you conform a spec to some piece of data, it automatically breaks apart all of that data into the parts that you're expecting. So it's great for parsing. It's also great for enforcement and for error generation. So this is a very powerful piece of Clojure that was recently added. It's also interesting because it creates a bridge to other sorts of solvers. You could very easily imagine Clojure spec being connected to a stat solver, for example, to show more interesting properties about your system. Okay, now let's switch gears a little bit and just talk about Clojure from a software engineering aspect. And throughout the slides, I've said things like modern language and so on. You know, and Clojure really is a modern language built for modern infrastructure to build modern systems. Largely, when I'm given a problem from some enterprise-style application, it's about taking some stream of input data, you know, operating on that data somehow and shoveling off that stream of output data to some other system. And I often need to do that in ephemeral computing on the cloud or really robust, large, multi-core, heterogeneous computing clusters. And Clojure sort of has embraced all of that your job really is about shaping data, and that you need to be embracing modern infrastructure on sequences of data. The first class specification and instrumentation is very powerful as well. We're seeing all sorts of interesting applications of that in the Clojure community itself. And Clojure has embraced design by contract. You can put pre and post invariants on all of your functions if you want, and those pre and post invariants can also just be generic specification orients. There's robust testing inside of Clojure that spans from standard unit tests that you would expect in any language to generative property-based tests. And the Clojure community has really embraced simulation testing for large distributed systems. And using things like Clojure spec and other aspects of the language can actually give you the generative property-based tests for free. That part of their specification allows them to generate the properties for those tests. Clojure is organized by namespaces, and so oftentimes Clojure code is architecturally evident. You know, you don't have this big splat of code sort of just everywhere that doesn't really make sense. It's hard to understand how it's all connected. Clojure code tends to be very architecturally evident just by a side effect of some language construct, in this case namespaces. And the lack of syntax and the lack of language constructs in general means that Clojure code has relatively low cognitive load. It's pretty easy to look at any piece of Clojure code, especially with the absence of reader macros, and make sense of it in a pretty short amount of time. Clojure code tends to just be about small operations that you string together at different points in your system. So those small operations are pretty easy to read through. The last point on this slide is about Clojure really embracing the ecosystems that it sits on. Now, if you've really invested in a lot of Java libraries or JavaScript libraries over some window of time, you want to be able to leverage all of that utility inside of Clojure. You shouldn't have to rewrite all that. You shouldn't have to reinvent all of that and so on. So, Clojure really focuses on frictionless integration with the host and still allows you to use all the value from those existing ecosystems, from those existing libraries and so on. There's a lot of interesting aspects to tease apart. There could be a whole talk just about the software engineering aspect of Clojure, but just one slide here. And just some quick aspects about the community and the general ecosystem for Clojure-specific tooling. If you're looking for the mailing list or for Slack or IRC or general events, there's a whole community section on Clojure.org. If you're looking for docs or examples of single one-off functions, there's a community-driven examples and docs site called clojuredocs.org. Clojure has really great IDE and text editor support pretty much across the board, and all have interactive development support. So it's true in Lisp. It's true in Clojure as it's true in many other lists that typically you connect your editor or your IDE to a running instance of your actual system and you sort of develop it live. Very true in Clojure. Project tooling is pretty standard project tooling based on whatever platform you're on. So for standard Clojure on the JVM, that's Maven or Gradle, or the Clojure-specific tools like Boot and Lanigan. If you're looking for professional services, support, or training, that is provided by Cognitect and other companies. If you're trying to build robust web services, there's a great library for that called Pedestal. And if you're looking to see how you might use Clojure's constructs or Eden to rapidly create microservices, there's a library called Vase. Also, there's a separate Maven repository just for Clojure code called Clojures. And you can actually discover more libraries based on their domain or their specific purpose at a site called Clojure Toolbox. So let's talk about Clojure being applied. We're going to go through these examples really fast and move on to questions here. We're getting pretty close to that time. But let's start with Walmart Savings Catcher. So this processes and integrates every purchase across all of Walmart. So more than 5,000 physical stores, all online purchases, all mobile purchases. It's a globally distributed system with globally distributed data sources, all written in Clojure. This one system powers Savings Catcher, Voodoo InstaWatch, and the Black Friday 1-hour guarantee. It has gone through multiple Black Fridays at this point with absolutely zero hiccups. And perhaps what's most impressive is that it only took 8 developers to write this entire system. So here's a very large distributed data fusion problem that Clojure really helped to tame. And the Boeing 737 MAX diagnostic system is also written in Clojure, another very interesting data fusion application. The diagnostic system superficially very similar to your check engine light, except there are hundreds of sensors, streams of data, constant calculation. That calculation could be value validations based on the sensors or interdependent rules between different parts of the plane. There are over 6,000 possible codes that this thing can generate, but sort of the impressive part about this is this entire system is only 34,000 lines of Clojure, so not that big considered to other enterprise or other industrial diagnostic systems. It's fully integrated into the flight deck as well as the ONS system, so all of the laptops and tablets used by the flight crew and the mechanics, this publishes to all of that. So not only is it checking data, but it's also publishing data. And a quote from the case study, Clojure is a relatively new language that allowed us to write rules and code capable of handling massive amounts of data under significant hardware limitations. So data fusion, sort of quote unquote in the small in a very interesting aspect. And that same report also captures significant cost and savings time, as well as improved error detection and accuracy to the older system. But anytime that you have a data-oriented problem, including trading or financial information, Clojure seems to be a really great fit. DRW trading was already on the JVM. They already had all these libraries and existing systems in Java, and they really needed speed. They really needed fast execution performance. But more importantly, they also needed to be able to see a result of the market, code something up, and get time to value to be as quickly as possible. And Clojure was there for them through and through. So their domains were obviously very much dominated by data, and the data-oriented abstractions really helped simplify the solutions as they moved forward. So that's all I have for the overview of Clojure. I hope that was very helpful. Let's go on and move to questions.
Yes, thanks a lot, Paul. Yeah, as you said, let's move on to questions. So let me kind of go through a couple of questions. So there are a few questions that are about, how does Clojure compare to kind of some other language? For example, how does Clojure compare to Common Lisp and typed scheme or typed racket? And how does core async compare to CSP and Go?
Okay, sure. Yeah, those are some great questions. So let's take that first one first. Clojure does a few different things than Common Lisp. So Common Lisp is a Lisp 2, Clojure is a Lisp 1. So there's some of these sort of superficial one-off differences. And there are also some different sets of trade-offs. So you'll notice there's a little bit more syntax in Clojure. So the data structures themselves, like Eden, exists as the serialized form of Clojure. So we have curly braces, we have square brackets, and so on. There's also no reader macros. On the Clojure.org site, there's actually a whole sort of side-by-side comparison of the different trade-offs and the differences between Common Lisp and other schemes and Clojure itself. On the sort of typed racket side, Clojure also has a typed form called core.typed. So we can do many of the same things that typed racket does, and is actually an open space for more innovation. There's a PhD student who has been working tirelessly on typed Clojure and moving that project forward. But with the creation of Clojure specs, there's been less emphasis on the typed Clojure side. So interesting comparisons there, but also, Clojure spec tends to be a little bit more interesting to people in that space. Onto the CSP and core async side. I mean, core async is almost one-for-one the same CSP system as Go. The real difference is that channels are many-to-many channels, and there's a separation of the buffer in the channel itself. So you can define different buffering aspects to your channels. They could be fixed size buffers, they could be sliding windows, dropping buffers, drop the earliest, drop the latest, and so on. But you have Go blocks, you have put and take, but again, the channels are many-to-many. Again, on the core.async project site, there is a comparison directly for Go and core async.
All right, so the next kind of group of questions is about Clojure versus Java. So for example, Java 8 also has a lot of the kind of functional programming style things with lambdas and stream processing. And then the other related one is comparing Clojure with Spark.
Okay, sure. So I actually give Clojure workshops quite often around the country, and everybody always asks the Java 8 and Clojure comparison question, because Clojure 8 has done a lot, especially with streams and sort of the stream-oriented stuff, and getting handles to static functions makes them, or static methods makes them feel sort of like first-class functions and lambdas and so on. So what's the real difference? And the real difference is that all of Clojure is built around a value-oriented system, just about data, specifically about immutable values. And so with streams, streams are have to be necessarily destructive. They have to be compatible with all the iterators that already exist inside of Clojure and so on. So you see some key differences between embracing immutability and using all the aspects of immutability to leverage the system versus the fact inside of Java 8 that things are still mutable by default. Things are still destructive. You still have to eagerly process things, and when you process them, you've destructively gone through them and so on. And so really, the core thing, you go back through the slides and you look at that mutable versus immutable, transient versus persistent. Those are the key aspects that still hold true regardless of the language features that were added. The second piece is, Java developers had to wait all the way until Java 8 to get that functionality, right? And I'm sure they actually still want more. And in Clojure, you don't have to wait for anybody. If you want to change the language or add a new processing capability or new programming model, that's just a library, and maybe somebody has already written that for you. And so it's sort of the best of both worlds in the Clojure world. And Clojure related to Spark, well, Spark is a full, data processing library. So it's not really a programming language, although it has aspects, I guess, of a programming language. But you can use Spark inside of Clojure. If the question's more about, what's the compatibility between Clojure and Spark, compatibility is great. There's actually a dedicated library for using Spark. And on the Cognitect website, there's a case study about using Spark and Clojure and Datomic all together to create very interesting computational pipelines and data processing pipelines. So yeah, you can take the same sequence abstraction inside of Clojure and run it on top of Spark. That's effectively what the library does.
All right, so we're running out of time, so I want to do one last question, and I'll take a very geeky one as the last one. And that one is if Clojure is properly tail recursive.
So Clojure's tail recursion is limited by whatever platform it's on. So there's no There's no proper tail recursion on the JVM. And to get around that, there is a recur function, a recur call that exists inside of Clojure that allows you to recur back up to a loop spot or to a function spot. And that same thing can be extended into trampoline, so you could trampoline between two pieces without moving through the stack. So it's really limited by the platform. Again, on the Clojure.org site, there's a whole dedicated subsection just about tail recursion to explain that fact. So yeah, that's sort of the short answer.
All right, so I'm afraid we have run out of time today. I'd like to thank Paul again for his great presentation and insightful answers to the questions. And a special thanks, of course, to all the participants for taking the time, you know, in your busy day to attend and kind of like ask questions. And please remember that the webinar was recorded and will be available in a few days at webinar.acm.org. And there you can also find announcements for upcoming webinars. Don't forget to fill in the survey, because we use that to figure out what future topics or speakers you would like to see. And on behalf of the ACM, Paul deGrandis and myself, Eric Meyer, thanks again for joining us and hope to see you again in the future. This concludes the webinar for today, and thank you all, and bye-bye.